Welcome to Signals and System subject classes. Now we are in the sixth chapter, that is discrete time Fourier transform. So this is the fifth video. So in the last 1 to 4th videos, we finished the details about the discrete time Fourier transform. So in this class, so I would like to revise the whole chapter in this one video. So this is a revision class. So in the first, in this revision, so you know that here I'm writing discrete time Fourier transform pairs. See, this is x of n. It is a discrete time. It is discrete time signal. And x of e power j omega, it is a discrete time Fourier transform of the discrete time Fourier transform of x of n. So this is the time domain signal, this is frequency domain, that we know that. Next, the formulas for the Fourier discrete time Fourier transform, that is x of e power j omega, so that equal to sigma x of n from the minus infinite to the plus infinite into e power minus j omega n. That's it. Then inverse Fourier transform, that is x of n, its formula already we discussed in the previous classes. So that is equal to 1 by 2 pi integration. Why we are doing integration? So this is x of e power j omega. Discrete time Fourier transform is a continuous signal, and it is also periodic. So that's why we should do the integration within the one time period only. X of e power j omega into e power j omega n into d omega. Why? Because this frequency domain, it is a function of the omega. So we go for the properties. These properties, so before writing the properties, so here I'm writing the, I'm taking the two signals. One is x of n. So the corresponding Fourier transform, so that equal to x of e power j omega. And another one, that is y of n. So it's Fourier transform y of e power j omega. So these are two signals. It's discrete time Fourier transforms. Discrete time Fourier transform. The first property is linearity property. So the linear property, see, so a into x of n, here I am directly writing, I don't want to explain. So this is a revision class. So this is discrete time. So the corresponding A into x of e power j omega plus b into y of e power j. Whatever we studied in the 1 to 4th videos, I would like to write in one place that is useful for your preparation. The next one is time shifting property. So time shifting property. So that it could be, so x of so n minus n naught. So it is x of e power j omega is multiplied by the e power minus j omega into n naught. The next one, frequency shifting. Frequency shifting. That is nothing but x of n is e power j into omega naught into n. So this is multiplied for shifting in the frequency domain. What is the shifting? Simple, x of e power j, here omega, so omega minus omega naught. For the case here plus, we are taking the place. The next one is complex conjugation. Complex conjugation. In the complex conjugation, you take x of n complex conjugation, then the corresponding Fourier transform, that is nothing but x of complex conjugation, and also j omega must be replaced by the minus omega. That is the difference. The next one, time reversal. So in time reversal, x of minus n, same. So n is replaced by n minus n. Then omega must be replaced by the minus omega. That is the difference. So just replace the x of e power minus j omega. Next one, time expansion. Time expansion. So x of n k. So that equal to. So this is, we can write n by k. So this is for case n is multiples of k. 0 for not multiples is not multiples of k. So for this case, so k here, so k come to the in multiplication in with the frequency that equal to j into k into omega naught. So convolution. So convolution property, x of n into, sorry, convolution in the time domain. So this is the symbol for the convolution, x of n, y of n. So multiplication in the frequency domain. X of e power j omega into y of e power j omega. Next, multiplication. So multiplication in time domain, its corresponding frequency domain must be convoluted. So the multiplication, so x of n, y of n, the convolution here, I would like to write a formula that is 2 pi integral 2 pi, the convolution between the frequency domain. So first change variable x of e power j theta y of e power j omega minus theta into d theta. So this is the convolution between the, so then you can write, so this is the formula for the x of e power j omega convolution y of e power j omega. Then we go for the differencing. The differencing property, differencing. So differencing, so x of n minus x of n minus 1. So it's discrete time Fourier transform. So that is 1 minus e power minus j omega n naught equal to 1 into x of e power j omega. The next one is accumulation. So in accumulation is nothing but summation. So x of k from minus infinite to n. So its accumulation property. So discrete time Fourier transform. So similar same. So here this factor is multiplied. So how to prove that in GP? For the, this is nothing but x of n plus x of n minus 1 plus x of n minus 2, like that. Then for the shifting, apply the time shifting property, we'll get the GP. The ratio in GP, the ratio equal to e power minus j omega. So it goes to infinite. It goes to infinite. Then directly 1 by 1 minus e power j omega. So x of, this is for the x of n, and the GP, the sum of the e power minus j omega, that equal to 1 by 1 minus r equal to e power minus j omega. Then the constant, for the constant we should write x of e power j into the power of 0, and so this is, so this period discrete time Fourier transform, it is a continuous and it must be periodic. So we should take impulse chain, but in case of the continuous, we have taken only one impulse. So this is impulse chain. So omega minus like k into 2 pi. So here the k equal to minus infinite to plus infinite. So because of this impulse chain, this is the periodic. Next, differentiation. So in time domain, it is a discrete. We can't do the differentiation, but discrete time Fourier transform, it is in the continuous. Then we can do the differentiation. So for that, this is differentiation. differentiation in in frequency domain. You should write in frequency domain. So in frequency, so directly here I'm writing that is we got n into x of n. So this is discrete time Fourier transform. So j into d by d omega into x of e power j omega. So this is the case. So the next one, conjugate symmetry. So this is enough. So conjugate symmetry, in conjugate symmetry. So x of n, this is real. So then real, it's Fourier transform conjugate also that is equal to, so see, after complex conjugation of this one, its Fourier transform is nothing but x of x complex conjugation in e power minus j omega. Then it complex conjugate also we will get the x of n. So it is equal to the x of e power j omega. And previously we learned that complex conjugate of the x of n is nothing but its corresponding Fourier transform. This is, so the complex conjugate, this is real. So the complex also will get same x of n. So this must be equal to the its Fourier transform. So next, the real part of x of e power j omega and its time reversal real part also same. So real part of its time reversal. So time reversal Fourier transform is nothing but omega must be replaced by the minus omega. So these are so two real parts are equal. Then imaginary part. So imaginary part of x of e power j omega. So that equal to minus imaginary part of x of e power minus j omega. Next, mod of, so the magnitude of x of e power j omega. So that equal to mod of e power minus j omega. So its magnitude also equal. But there is a 180 degrees phase shift between these two. So x of e power j omega, so that equal to minus x of e power minus j omega. The next one, real and even. Real, even signals. So x of n, this is real, same similar to the already same we discussed in the continuous time and discrete time Fourier series and continuous Fourier transform, same thing. So real and even. So x of e power j omega also real and even. Until unless it is odd, so there is no change, real and even. So see the next case. So real and odd. So this x of n real and now odd. So now, so it is changed from the real to the purely imaginary. Now it's Fourier transform purely imaginary. purely and it is a odd. And even and odd decomposition, even odd decomposition, decomposition of real signals. So the even part, so this is even part, means it's a even part of x of n. So it's a discrete time Fourier transform. So that equal to, so real part of x of e power j omega. The next odd part. So odd part of n equal to odd part of x of n. So j into imaginary part of x of e power j omega. The last one, Parseval's relation. Here I'm writing Parseval's relation. This is the last property. Parseval's. So I think in this subject, this is the last Parseval's. Then next time we will not hear this word Parseval's. This is the last. This is the fourth time. So Parseval relation is nothing but energy relation between the time domain signal and frequency domain. So left side here I'm taking the x of n, and the right side x of e power j omega, and this is about so first write down x of n formula. So x of n formula is nothing but 1 by 2 pi integral of 2 pi. So this is energy nothing but integral of power. So power, so mod square, it gives the power. So in formula, x of n equal 1 by 2 pi integral of x of e power j omega into e power j omega n. So the mod of exponential goes to 1. The last term is omega. Now write down the formula for x of e power j omega, that equal to sigma n from minus infinite to plus infinite x of n into e power minus j omega. So, so we should write the power. So power is number square, the mod of square, and the mod of exponential goes to 1. So this is Parseval's relation. Then formulas. So, so in first, I want to write in first periodics. Periodic in continuous also for periodic signal. So first column for the x of n. The next one is its Fourier transform. X of e power j omega. The last one is Fourier series coefficient. So these are the columns. Now the first one is I'm taking any random signal. So this x of n we can write in Fourier series representation ak into e power jk omega naught into n k within the time period. So it's Fourier transform. So periodic signal, we know that 2 pi into ak. So ak into 2 pi del of omega minus k into omega naught. Here k, here also ak is a periodic. So this is enough. So AK for all values, same. First, another periodic signal, that e power j into omega naught into n. So it's so that a1 existed, that equal to 1. Otherwise, other all values ak equal to 0. Only a1 only, it is having only a1 only. So for that, 2 pi, so a1 equal to 1, then del of omega minus, I am writing here the omega naught equal to 2 pi k, this is sigma actually, pulse strain, del of omega minus 2 pi L. So L from the minus infinite to plus infinite. So cos omega naught, so pi into sigma L minus infinite to plus infinite, del of omega minus 2 pi L, sorry, 2 pi, so shifting, sorry, this is also shifting, omega minus omega naught minus 2 pi L. So omega minus omega naught 2 pi L plus del of omega plus omega naught minus 2 pi L. So this is so similarly sin omega naught n, so pi by j sigma L from minus infinite to plus infinite. So del of omega minus omega naught minus 2 pi L, but here we will get the minus only. So del of omega plus omega naught minus 2 pi L. So this is sin omega naught. So for the one, so this is we have taken from the this formula, that equal to 2 pi sigma del of omega minus 2 pi L. So L from minus infinite to the plus infinite. So this is the case. Actually, there is no place for writing the Fourier coefficient, is it? Next periodic signal, that is x of n. It is a fundamental signal, rectangular pulse train. 1 for the mod of n less than n1, and 0 for the n1 to the mod of n half of the time period. For this, we know that the Fourier series coefficient ak, that is sine of k omega naught into n1 plus, here I'm writing, that is ak, so ak equal to sine k omega naught plus n1 plus 1 by 2 capital N into sine k omega naught by 2. So same substitute here. So the Fourier transform formula 2 pi ak already we have written here. That's ak into del of omega minus k into omega naught. So k minus infinite to the plus infinite. Actually, this is from minus infinite to the plus infinite. Next, impulse train. x of n sigma del of n minus m into n. So this m from minus, so this is impulsion, so m minus infinite to the infinite. So here the AK value, AK Fourier quotient AK for this impulsion that equal to 1 by n. This is the n time period. So n is a AK is a constant. So that's why here writing here. So 2 pi by n. So sigma del of omega minus k into omega naught into k from minus infinite to the plus infinite. So this is the periodic signal. The next we are going for the aperiodic. So in the aperiodic signals, first I'm writing the rectangular pulse. Rectangular pulse x of n equal to 1 for the mod n greater than less than n1, 0 for mod n greater than capital N. So for in this ratio there is no signal. For that Fourier series transform x of e power j omega that equal to same here. So sine omega into n1 plus 1 by 2 by sine omega by 2. Same here. X of e power j omega that is 1 for, so this is a periodic signal. Then 0 to mod omega from the pi. Next pi to the 2 pi. Okay. I think this is W. That is 0. So same sine Wn by pi n. So this is we have done in the continuous time. Actually, I didn't explain this formula. You know, you can get this formula from the discrete time, inverse discrete time Fourier transform. Okay. Once check it, this formula. Okay. Then del of n. So del of n. So Fourier transform equal to 1. Del of n minus n naught Fourier transform e power minus j omega to n naught. U of n, that U of n equal to 1 by 1 minus e power minus j omega. Same U of n we can write in terms of the impulse. Then so accumulation property, in the accumulation property x of e power j omega by 1 minus e power j omega plus pi into x of e power j omega that goes to 1. Then del of impulse in omega minus 2 pi k. The k from the minus infinite to the plus infinite. So similarly, a to the power of n, e of n, that formula 1 by, here we will get the 1 by a into e power minus j omega. So here no need to write this. Is it? Leave it. No, it doesn't matter. Next, differentiation property, differentiation in the frequency domain. So that equal to n plus 1 into a to the power of n e of n. This is nothing but 1 by 1 minus a into e power minus j omega square whole square. This is from the it is written from the discrete time also. Differentiation in the frequency domain. So similarly, so n plus r minus 1 factorial. So this is a variable. This r is a constant. So n factorial into r minus 1 factorial into a to power of n into e of n. So this is n power goes on increases in factorial. So this is a factorial. So that equal to 1 by 1 minus a into e power minus j omega to the power of r. So this is the case. So it is about discrete time Fourier transform revision. So here in this video, I have given complete information. So this video. It's very useful while preparing your examination in the revision time. In the next class, we will start Laplace transform. That's beautiful chapter. Why? Because this Laplace transform we are using in many subjects like network theory while designing the transient analysis and in coming to the control system, the total control system that everything it is explained with the help of the S domain. So this Laplace transform, it is very useful for any examination. You take any examination, minimum 1 or 2 questions is compulsory from the, especially from the Laplace transform. Then we will discuss Laplace transform in the next class. Thank you.